Estamos live. Podemos começar.
Pronto? Okay. Then we will start now the second session of SBESC 2021, Multicore and Performance Evaluation. The first paper to be presented is called Using Gem5 Simulator to Support Designing Space Exploration Targeting ARM Architecture. The paper will be presented by Iago de Oliveira Silvestre.
Hi there, my name is Iago de Oliveira Silvestre, and I would like to present the work that was submitted to the 11th edition of SBESC. This work is titled Using Gem5 Simulator to Support Design Exploration Targeting ARM Architecture, and was done under orientation of Professor Leandro Becker and with the support from Professor Antônio Carlos Beck. This work is part of Provant, a collaborative project between the Federal Universities of Santa Catarina and Minas Gerais. First and foremost, I would like to discuss the motivations behind this work. The performance analysis of embedded systems is critical when dealing with system deadlines. These embedded systems can vary in multiple ways, such as the CPU, memory, the operating system and kernel, and other input-output devices. So a study on how changing these components would impact overall performance would be greatly productive. The main objectives of this work were to use Gem5 to determine whether the developed software for proven project could be executed within their deadlines, and explore hardware and software changes that could be made and what performance changes are expected, while also verifying Gem5 simulation data precision, demonstrating how the simulation results can be useful to help guide hardware choices, analyzing the impact of cache memory usage and exploring alternatives, and also providing an easier way to set up ARM architecture simulation. With that out of the way, we can take a look at what this presentation will contain. First, I'll talk a bit about the Gem5 simulation tool and what it offers. Then move on to explain what we try to accomplish by implementing a Google Colab environment. I will also briefly explain the system under test, discuss the software that was chosen to be tested, and also the hardware-based configuration. We can then start to discuss the results found both in Gem5 simulation and real hardware tests. Finally, it is important to show some conclusions that can be drawn from this work, and a few of the possible future works. The Gem5 simulation tool originated from the merging of two tools, the M5 from the University of Michigan and GMS from the University of Wisconsin-Madison. So this tool offers various CPU and memory models that differ on the level of accuracy. Complex CPU models include the simulations of CPU branch predictors and instruction pipelines, and this tool also supports a high variety of instruction set architectures such as ARM, RISC-V, x86, Alpha, and others. So this tool offers basically two simulation modes. A syscall emulation mode, where the system services are developed by the tool, trading lower accuracy for higher simulation speed, and a full system mode, which is depicted on the picture, that allows the user to simulate a complete system with its components and operating systems. So basically, what we feed to the Gem5 simulation is the kernel, the image of the operating system, and the simulation parameters. Gem5 also offers a very useful library called M5Ops that can be added to your program rather easily. This library allows the user to determine the part of the program where the simulation tool should collect the performance data. For example, in this picture here, we are using the commands reset sets and damp sets to select the function that we want the performance data to be collected. Before going into more detail of the system under test and results, I would like to talk about the Colab implementation. We noticed during this work that Gem5 requires a decent amount of work to set up. wanting to make this process easier, we made a Colab implementation where the process of installing Gem5 is automated. We also import files that take a long time to build, such as Gem5 simulation binaries and simulation checkpoints, which cuts the setup process significantly. This implementation also offers options for more familiarized users, and it currently supports ARM but could be expanded. We chose three control strategies from the problem project to study: the LKR, the mix of H2 H-infinity, and the adaptive mixing. They were all developed in C++, all used the Eigen library for matrix operations, and ROS to package sensor communication, and they all had a 12 milliseconds control window. They varied, however, on control technique and other things such as feed-forward implementation. These control programs are available in our GitHub. For the simulation hardware parameters, we chose the Raspberry Pi 3B Plus. We chose this configuration in order to compare the results from the simulation with the results from real hardware tests. Regarding the OS image file and kernel, the tests executed in this work used the compact ARC64 OS image file and a Linux kernel provided in this link. We also used the HPI CPU model, the classic memory model, and the Gem5 fast simulation binary. So first, let's check the LKR control program results. This program executed very quickly with an average control loop time of 1.5 microseconds. It also showed very low percentage of CPU idle cycles. When we analyze the instruction types executed during this control program, we also see that there were very few floating point unit operations. This data, coupled with the great performance in the first picture, may suggest that the CPU with a dedicated FPU chip, such as the Raspberry, might not be needed for this control program to execute well. The LKR control program also showed very low mismatch between the execution times obtained from simulation data and from the real hardware tests. The average mismatch in the first 10 control loops was of 2%, and the worst mismatch occurred in the first control loop, where the Gem5 executed with a mismatch of 14%. Going to the mix of H2 H-infinity performance, we see very different results. This control program had an average execution time of 2.25 milliseconds, with the worst execution time being around 6.6 milliseconds, getting dangerously close to the 12 milliseconds control window, when we consider that the control thread will compete for the CPU with other threads on the embedded system. We also see a very high percentage of CPU idle cycles, which normally means the CPU is waiting for data to be fetched for it to conclude its calculations. We can also notice the rather high reads and writes on the RAM memory for a control program, with an average of around 2 megabytes of data read from the memory every control loop. Finally, going to the instruction types, we see that here the floating point unit operations were more present, indicating that a CPU with a dedicated chip for FPU is probably a necessity for this control program to execute well. When we compared the simulation execution time for the first 10 control loops with data from real hardware tests, we saw an average mismatch of around 5%, with the worst mismatch occurring in the first control loop, where Gem5 simulation data had a mismatch of 117%. For this control program, we also ran some additional tests on the real Raspberry Pi 3 board. We used the perf tool to collect CPU data such as level 1 and level 2 cache loads and misses, total CPU cycles and instructions, and of course execution time. What we saw was that when we compared the Gem5 simulation results and the perf data collected from the Raspberry board, we had similar results, with an exception of level 1 data cache misses, which showed a big mismatch of around 85%. Finally, going to the last control program tested, the adaptive mixing, we saw a control program which had great performance. These results are discussed further in our article, but basically it showed an average execution time of 170 microseconds, well within the 12 milliseconds control window. It also showed a low percentage of CPU idle cycles. When we compared the data from the Gem5 simulation tool and the real Raspberry Perf tool, we saw similar results as the H2 H-infinity mix. Most of the CPU data was fairly similar, with the greatest mismatch being the level 1 data cache misses, where the Gem5 simulation tool had a mismatch of around 98%. When we compared the execution time of the first 10 control loops for the adaptive mixing control program, we saw an average mismatch of around 36% from the Gem5 simulation data and real hardware test. This was also the first control program to show a relatively high mismatch that wasn't only on the first control loop. For this control program, both the first and sixth control loop showed high mismatch. In literature, cache memory is normally discussed as a problem to achieve determinism in a program performance. To tackle this problem, we tried implementing software prefetching, but at least as it was implemented, this did not show any significant impact. We then checked through simulation what performance impact was to be expected from the removal of cache memory. As expected, this showed a great impact on performance. We tested the two poorest performing control programs, the H2H Infinity Mix and the Adaptive Mixing. Both showed a big increase in execution time, reads and writes from the RAM memory, and of course CPU idle cycles when we remove the cache. So, a few conclusions that can be drawn from this work are: Gem5 was a valuable asset to determine control program performance with relatively good precision. This tool can be used for multiple ends, but one that is very noticeable is the ability to test how different hardware configurations can impact a program performance. We also saw that Colab offers a significantly easier way for non-experienced users to execute simple experiments. The cache memory also showed great impact on the tested control program's performance. And finally, Gem5 was successful in evaluating design alternatives for projects using the ARM architecture. And to list a few of the possible future works, we can check the impact of changing the instruction set architecture on both Gem5 precision and program performance. We can explore the use of customized operating systems to reduce the amount of background processes. We can further study the comparison between Gem5 and onboard results. We can use sensor data from the Gazebo simulation environment to diversify the UAV states, and with that increase coverage of the control program. We of course could improve the Colab implementation, for example using different instruction set architectures and different Gem5 simulation binaries. And finally, we can explore the use of Gem5 to determine system scalability, where different processes are competing for the CPU.
Okay, then, welcome Iago. Nice presentation. Questions for Iago? You can. Oh, Leandro, okay.
I have a quick question. You mentioned that you had 85% of difference between cache misses between
Márcio, só para testar o áudio,
simulation.
eu não estou escutando. Você está falando?
No, actually, George is making a question. You can proceed, George. Yeah.
Acho que o Jorge está ali. Bom, deve ser problema no meu
Can you
áudio.
hear me?
Não estou escutando.
Can you hear?
George is making a question. Did you hear?
Yeah, but can you guys hear me?
I can hear you, George.
All right. Okay. So if I didn't miss anything, Yaro said during his presentation that there was a 85% difference between Gen 5 and Raspberry Pi in terms of cache misses, even though you found a very quite similar figure in terms of cycles, yeah, execution time. So I was wondering, how could you explain this? Because cache miss codes, I mean, may increase a lot execution time. So 85% of difference seems a quite good number to explain a quite high difference in terms of execution time, and you didn't see this difference. So can you give some hints about what? Sorry, I cannot hear.
Yeah, I can also not hear you. Are your microphone set on? Iago? Okay.
Just to collaborate, I had to disconnect and connect again. Maybe there was some, because my mic was not working.
Do you guys hear me now?
Okay.
Oh, yeah.
Yeah, now it's okay. Yeah.
I had to reload as well.
Okay.
So, George, was it?
Yeah, George.
Yeah, George.
Yeah, we're still trying to inspect what was the main result, what was the main source of this disparity between the cache misses. One thing that we are trying to check is because the method that was used to collect these cache misses was through the perf collect tool. So we're still not 100% sure if like the background processes running on the Raspberry Pi are affecting the cache misses, but this is certainly one of the most important problems that we are trying to check, because as you said, cache misses are very important on execution time, and there was a huge disparity between the two sets of data.
Mm-hmm.
Okay. It's when we did some experiments, we saw that there was a set of events that is that explain how much the CPU waits for something to occur. For example, if a cache miss occurs, there might be no instructions to execute in the pipeline, in the processor. So the processor has to wait for this, and perhaps the increase in cache miss are being compensated by other parallel things that are going on. And perhaps could be a hint, I don't know. And another question that I'd like to make is the point. Control loops are quite simple kind of programs to run. Did you try to do anything different with other kind of benchmarks?
Yeah, we are at a certain point of this study. We were trying to think of different programs to diversify. We haven't run any tests so far, but the main idea that was proposed was to do some form of image detecting, the image processing, which would be significantly higher complexity programs. So as well to verify if Gem5 is suitable for these programs that should take more time to execute.
Well, thank you very much, and thanks for the super work. And perhaps we should talk offline, because perhaps we have complementary.
You can also write the questions in Mattermost, right, George?
Yeah.
You can put the questions there. Yeah. Leandro, do you want to?
No, I just wanted to thank George for the questions, and I'm sure we can continue some offline conversation also, because it matches with the work you presented in the morning, so it's great.
Okay, very nice. Okay then, thank you again, Iago. We should go to next paper. Second paper of this session is Cryptography on Untrustworthy Cloud Storage for Healthcare Applications, a Performance Analysis. Paper will be presented by Lúcio Reis.
Hi, I'm here. Can you hear me?
Yeah,
Okay, great.
Starting your presentation. Okay.
Hi, my name is Lúcio Reis. I'm a student at the Universidade Federal Fluminense, Niterói, Brazil. I also do scientific research at Amsterdam University Medical Centers, University of Amsterdam, and I'm here today to present our work, Cryptography on Untrustworthy Cloud Storage for Healthcare Applications, a Performance Analysis. This is the summary for today's presentation. I'll go through contextualization, problem and motivation, research question, experiments, results, and conclusion. So starting with contextualization, we have clouds, which you can define as large server infrastructures that are connected to the internet network, providing ubiquitous computing. We have examples of public cloud providers such as Google, Azure, and Amazon that offers their infrastructure as a service, and we probably use everyday applications that are hosted on those clouds. And they have a huge role in healthcare because they provide data sharing, which enables data availability of the patients and also improve healthcare quality. So in this work, we have two use cases for contextualization. The first one is the acute stroke care, which is the treatment of a patient when he suffers a stroke. So usually this patient needs to contact a call center, then the ambulance picks him up and brings him to the hospital. Therefore, a lot of professionals are involved in the treatment timeline, and they need to access the patient's data and do this through computers, tablets, and smartphone. And this need to be fast because, yeah, we have a slogan that time is brain because the time matters. Second one is the sleep medicine. This is the use case where the patients are recorded during their sleep. So therefore, we know what's happening to them during sleep and can provide treatment. It's not so dependent on time, and this can be done in a lab or in the patient's home. And we gather this information and store them in computers and send to clouds. So problem and motivations. So what are the risks associated with public cloud providers? The first one is data leaks, which we can define as internal accidents or intentionally exposing confidential data. So this happens from inside the public cloud providers to the outside. Second one is data breaches, which is we can characterize it as external attacks to these cloud providers. And both have the same impact on the user, which is the privacy breach and the unauthorized access to his confidential data. And how can we prevent these risks? So the first thing that we can do is have a private cloud infrastructure. In this case, the organizations have to build their own infrastructure, therefore have their own cloud infrastructure. This requires a lot of investment because we have infrastructure, we have maintenance, security, and so on. And still does not mitigate the data breach and data leaks. So the second thing that we can do is cryptography, which we can define as turning some readable data, some patient record, into a data that is unreadable. So in this case, if we do this, the records are protected, and even if they are leaked or some data breach occurs, the confidentiality is not broken. So we have two ways of implementing cryptography on public clouds. The first one is a server-side cryptography. So in this case, the data is sent to the cloud and then it's encrypted. So we still require trust on the public cloud providers because they are the ones that will encrypt the data, so they have access to the data, the readable data, right, before the encryption happens. And the second one is the client-side cryptography, which is the case where we encrypt the data before we send them to the cloud. So the cloud receives this data already unreadable, and if something happens, the data is secured. So this brings us to our research question, which is how can we implement and what's the performance of client-side cryptography compared to server-side cryptography. So we have two ways of performing cryptography in the browser, in the client side. The first one is using JavaScript, and the second one is using WebAssembly. Usually JavaScript is slower because it needs more steps to run, and it's a non-optimized code that can be optimized during compilation, but it requires time. While WebAssembly is just a precompiled from C, from any low-level language that you can just glue to the JavaScript and run. So this is what we want: investigate the performance of both implementations approaches, and also compare them with server-side. So our experiments, we just run experiments using the web browser. So we run in the Chrome browser version 90.0. Our machine setup, it's a notebook Core i5 with 16 gigs of RAM. And we didn't look for better machines because this is already a configuration that will extract most of the JavaScript engines. And the cryptography scheme that we will apply for every experiment is the advanced standard encryption standard in cipher blockchaining mode with 256 bits key. Moreover, the experiments, we want to perform a performance comparison between JavaScript libraries. Then we'll get the fastest JavaScript library and compare with WebAssembly implementations and PyCrypto. PyCrypto, it's a low-level Python library for cryptography. And the third experiment, we will compare PyCrypto with simultaneous users. So we'll have parallel requests and see how the server behaves with workloads. So the file sizes that we'll use to perform this encryption and decryption will be 1 mega, 10, and 100. And for the simultaneous request, which is the third experiment with PyCrypto, will vary our workload from 10 to 50 users. So the first result regarding the JavaScript libraries, we have four libraries. So we have ASM-Crypto, Crypto.js, Forge, and SJCL. Note that the graphs are in logarithm scale. So we can see that ASM-Crypto won in encryption and decryption, and for a huge difference. Then we took the ASM-Crypto and put it against the WebAssembly implementation in C and one WebAssembly implementation in Go, and against with PyCrypto, which is the Python library. So in this case, the PyCrypto won in encryption and decryption, but it's for a very small difference against ASM-Crypto, which is quite incredible. And we had some nice performance for WebAssembly in C, but still PyCrypto and ASM-Crypto perform very well. So our third result about the simultaneous users. So we varied different simultaneous requests for the server-side cryptography with PyCrypto. We can see here that even though we grow the number of simultaneous requests, the average time to attend each request remains the same. However, our total time grows when we increase the number of simultaneous requests. And in the worst case scenario is that if we receive, let's say, 50 simultaneous requests and some request it's queued to be attended at last, he would take, instead of an average time, the total time to be attended. So this is one of the scalability issues and of server-side cryptography, and that may be a point of concern for healthcare applications that use this scheme. So in conclusion, we've seen that client-side cryptography has worse performance compared to the server-side. So it's not that much. SMCrypto performed really well for a JavaScript library, but yeah, still it's worse. We have that client-side cryptography has advantages in scenarios with simultaneous users, because while the server side needs to handle every request, in client-side cryptography, the cryptography is distributed among the users. So if you increase or decrease the number of users, it doesn't matter, because the encryption is taking place at the user's machines. And last, the client-side cryptography does not threaten the availability of data. Yeah, it has worse performance, but we've seen that the performance is really, really good with SMCrypto, and it's yeah. So that's it. Thank you for listening to my presentation.
Okay, thank you, Lucio. So questions for Lucio? No? Okay, I have just a curiosity. If I could understood well, you said that when you send data to the server, in the server-side approach, you send all the data unencrypted to the server. Is that correct?
Yes.
Why should one do this? I couldn't figure out.
Well, the problem of using server-side, you have different approaches to use server-side cryptography, right? You can, for instance, encrypt the data somewhere and send it to the cloud, and let's say store the keys and the attributes that you want to give to the users to access that data, and all of that can compromise the data because you have everything, let's say, in a centralized server. So, and you can use server-side cryptography for performing the bottleneck of your applications, which is basically you are not willing to encrypt the data in your device or wherever, and you want to use the elastic clouds to have more computer power, more hardware power to do so. So server-side cryptography, it's really, really good in that matter, because you can have, let's say, a lot of computing power for less cost than having having local hardware and something like that. So it's very common to use in that way, but the problem for us at least is that if we use in that way, we are allowing that the patient's data can be compromised, can be somehow leaked. So yeah, so that's the main goal, to see if the client side can support the same performance for encryption, right? Without harming the data availability, which is crucial for us.
Okay. No, because in your case, I didn't see a point to send encrypted data to the server, no? Because it doesn't. Why the reason to encrypt a data which should be or could be already corrupted? No? But okay, in your case, it's perfect. Yeah. Okay, nice. One more question? No? All right, then. Thank you, Lucio, for your presentation. Then we can go to our next paper. Just let me copy here the link. So, next paper is called Implementation and Evaluation of Adaptive Cache Insertion Policies for Real-Time Systems. This paper will be presented by Bruna Araújo.
Hello everyone, my name is Bruna Araújo. I'm a master's student of Federal University of Santa Catarina, and I'm going to present the paper called Implementation and Evaluation of Adaptive Cache Insertion Policies for Real-Time Systems. This paper was written by me, Giovanni Gracioli, Thomas Roda, Dennis Hornert, and Marco Caco. So the cache memory is one of the most popular mechanisms used to improve the average performance of the modern cyber-physical systems. Every time that required information is not in the cache, it must be placed from main memory in some line of the cache. So the replacement policy is responsible to choose the evicted cache line. However, the high time penalties that a cache miss can cause make of the cache a big source of unpredictability, directly impacting real-time systems once those systems need to meet strict time constraints. In the context of hard real-time systems, designing and implementing a near-optimal cache eviction policy is essential, as the gains in execution time have a direct impact on the scalability ratios and the utilization of the target platform. Standard and state-of-the-art cache architectures feature either the random policy, the first-in, first-out policy, or FIFO, the last recently used policy, or LRU, or the pseudo-LRU policy. The first two are simple to implement but has a bad average performance compared to LRU. On the other hand, LRU-based policies are susceptible to trash when the required application data is greater than the available cache. Because of this, Crash et al. Proposed simple change to the insertion policy to reduce the number of cache misses for memory-intensive applications. Named these new policies as Adaptive Insertion Policies. They are LRU Insertion Policy, as known as LIP, Bimodal Insertion Policy, or BIP, and Dynamic Insertion Policy, or DIP. Besides those policies had presented interesting results when compared to LRU, their impact on the scalability of real-time systems has not been studied yet. Moreover, the original DIP evaluation has not studied its behavior when varying the number of ways and the impact of the cache miss counter size. So, the contributions of this paper are the implementation of the adaptive cache policies into an open source cache simulator called CacheGreen. This way, we were able to extend the analysis of the DIP adaptive insertion policy considering the context of real-time systems, and evaluate the behavior of the policies when varying the cache parameters. Moreover, by applying the reduction on the number of cache misses of the DIP policy into the scalability analysis, we were able to observe its impact on the scalability ratio of real-time systems. The cache simulator used was the CacheGreen, an open source tool provided by Valgrind that requires as input the cache partition size, the number of ways, the line size, and the replacement policy, and generates a detailed profile of the whole cache hierarchy as the number of access and misses to the first and last level of the cache. Whenever there is an instruction or data reference, CacheGreen simulates the cache access using either an instruction or data cache. The target cache is passed as parameter in the call to the isMiss function, together with the address set and tag. Within isMiss, the appropriate cache eviction policy is applied for a function pointer to the function which implements the eviction policy algorithm. We modify this part of the CacheGreen by adding functions for each adaptive insertion policy. If there is a miss in the first level of the cache, then cache grind calls again isMiss, passing the last level of cache as parameter. This listing shows the implementation of LIP into cache grind. setNo represents the number of set, and CSOS represents the cache associativity. In line 3, the required tag is retrieved. If this tag is found in the cache, then it is promoted to the most recently used position and shuffle the rest down, as shown in line 6 and 7. In line 9 is show what happens if a miss occurs. So the incoming line is inserted into the LRU position, or the last recently used position. Now this listing shows the implementation of BAP. It's important to notice that BAP behaves as LRU or LIP for any cache hit by promoting recently accessed line to the MRU position, or the most recently used position, as is shown in line 3, 4, and 5. But when a miss occurs, BAP will need the bimodal throttle parameter to define how the policy will behave. Together with the bimodal throttle parameter, a randomly generated number, prob, are used to define the behavior of BAP. As shown in line 8, if this random number is greater or equal than the bimodal throttle parameter times 100, BAP will behave as LIP. Otherwise, it will act like LRU. The DIP implementation follows the global mechanism, which uses two auxiliary tag directories with copies of blocks from the main cache. In each directory, the LRU and BAP policies are applied exclusively. The policy used in the main cache is the one that counts the least number of cache misses in the respective directories. For this, a binary counter named pcell is incremented at every miss that occurs in the directory under the BAP policy, and is decremented whenever a miss occurs in the directory under the LRU policy. So, if the most significant bit of pcell is 0, LRU policy is used. Otherwise, BAP policy is used in the main cache directory. It's important to see that pcell is a binary counter and is always initialized in the middle of its range. So, for example, for a pcell with 4 bits, its range goes to 0 to 15 in bits. So, pcell is initialized in the 1000 that equals to 8. So, if pcell is greater or equal to 1000, it will be applied the LRU policy. If pcell is smaller, then the BAP policy will be used. For evaluation of the BAP and DAP implementation, two benchmark suites were used. MiBench suite represents soft real-time applications, and Cortex suite represents hard real-time applications. The benchmarks have been executed for a wide range of configuration, as the total cache size, the number of ways. The cache replacement policies used were LRU, BAP, and DIP. Additionally, in the case of DIP, the size of pcell is also subject to variations. However, the cache line size is fixed to 64 bytes for all the experiments. The PIP throttle parameter was set to 1/64. The first experiment evaluates BAP and DIP and compared them to a LRU with respect to the amount of cache misses each benchmark experienced for the policy. The figure displays the results for PCA small and SVD3 small. Each of these benchmarks is simulated in a platform assuming an 8-way associative cache with the total size represented in the horizontal axis, and for different eviction policies shown by the bar cluster, with LRU being the blue bar, BAP the orange bar, and DIP the green bar. The pcell counter has a size of 10 bits. The amount of cache misses for each cache configuration is reported on the vertical axis, and is normalized according to LRU. So, within each bar cluster, a smaller bar than LRU implies that the policy has fewer cache misses and thus a reduced execution time. A first observation from the results concerns the behavior of the DAP policy, that always tends to replicate the performance of the BESC policy between LRU and BAP for a given cache size as is expected with the global mechanism. Another observation shows that BAP and DAP are not always better than LRU. In each of them, we observe a range of cache size for each the amount of cache misses is smaller than LRU. These ranges vary from one benchmark to another. For instance, PCA small experience fewer misses using BAP and DAP for cache sizes ranging from 16 kilobytes to 512 kilobytes, while SVD3 presents best results in the range from 2 kilobytes to 8 kilobytes. These variations means that the efficiency of the adaptive insertion policy depends on the amount of data needed by the benchmark and the cache size. In the original paper introducing the DAP policy, the size of the pixel counter is arbitrarily set to 10 bits. However, its size can potentially influence the policy switching decision. So, the objective of this set of experiments was to evaluate the impact of the pixel size on the amount of cache misses occurred during the execution of PCA small benchmark. For this experiment, we assume a 128 kilobyte large 8-way associative cache and run the benchmark using the LRU, BAP, and DAP policy. We vary the size of pixel on the horizontal axis and report the amount of cache misses occurring on the vertical axis. Each bar is normalized over the cache miss occurring using LRU. PCA small is slightly affected by the pixel counter size, as we can see in the figure. For a small pixel size, DAP incurs more cache misses than BAP policy. However, as the pixel counter size increases, the gap between DAP and BAP fades away. We can conclude that the pixel counter size influences the execution of tasks and that a large size enables DAP to approximate the optimal choice of policy. The next experiment aimed to understand the relationship between the associativity of the cache, the eviction policy, and the amount of cache misses that a given benchmark will experience. The results are displayed in the figure. The selected benchmarks, PCI small and SVD3 small, both highlight a different behavior. In the case of PCA, we can observe that the amount of cache misses decreases linearly as the associative increases, reaching a plateau at 16 ways. The good performance of BAP can be linked to an extremely sequential workload with low data reutilization. On the other hand, for SVD3, the BAP policy fails to outperform LRU, hitting and workload with higher data reutilization. Globally, note that DAP is useful in always closely following the best performing policy. The objective of this experiment was to understand the evolution of the pixel counter during the execution of selected benchmarks. To this end, we instrumented our extended version of CacheGreen to collect and log the pixel counter content. In this set of experiment, we assume a 128 kilobyte large 8-way associative cache have a DAP for eviction policy and feature a 10 bits wide pixel register. The pixel counter is initialized with the value of 512, meaning that LRU is initially the policy selected. This frontier value separating BAP and LRU policy is drawn in red. Regarding the PCA benchmark, one can clearly see that evolution of the pixel value through the execution is segmented in two distinct areas. According to the pixel value before the 10,000 instruction, the LRU policy is applied. Thereafter, the BAP policy is applied, meaning that this policy is the most adapted to this section of the program. For the schedulability impact evaluation were generated 10,000 task sets. Each of them contains 8 tasks. We vary the utilization from 0 to 1 with a step of 0.01 to generate uniformly distributed random task utilization values that sum to the total utilization. For each task utilization, we randomly generated a parity value ranged from 10,000 to 1 million microseconds with log uniform distribution and obtain the task WCT. Tasks have implicit deadlines and are assigned priorities based on the rate monotonic policy. The task set for BAP and DAP are obtained from the LRU task set by scaling the task's worst case execution times by the scaling factors from PCA small and SBD3 small benchmarks. Figure A shows the scalability ratio where the scaling factors of all tasks are based on PCA small, and Figure B, the scaling factors are based on the SBD3 small benchmark. PCA favors BAP and the later LRU. The results for PCA show significant improvement of BAP over LRU, reaching over 50% for high utilization rates. For SBD3s, LRU only slightly outperforms BAP. Most importantly, in both cases, DAP always follows the best policy, incurring very little overhead. So in this work, we perform an evaluation of the LRU-based adaptive insertion policy, LIP, BAP, and DAP. For this end, we observed the impact of the cache geometry for each policy compared to LRU, and we investigate the impact of the counter-selector PCL in DAP. The obtained results from a simulation environment have shown that the cache size and the associativity play an important role in the performance of the adaptive insertion policy, while the variation of PCL size are not that important. As future work, we plan to implement and evaluate DAP in an open processor architecture such as RISC-V and explore the choice of cache-related parameters to improve the replacement policies, aiming at real-time applications. And that's it. Thank you all for the attention.
Okay, so questions for Bruna? No? All understood? Okay, Bruna, are you here? I can listen to you. Speaking? Oh, I cannot hearing you. Yeah, it seems that your microphone is open, but I can hear. Oh, strange. Yeah, I saw your mic is open, but I can't hear you. I don't know what did happen. Okay. Then I think it's better I will write the question for you in Mattermost. One question for you, Bruna. You that's it. George, are you hearing Bruna? No. I cannot. Okay. Okay. Bruna,
hello, Marcio. Maybe I can help and answer the question.
Okay.
The author of the paper.
Sure.
Yeah. Yes, George. The reason why we did not perform any experiments using like a preemptive scheduling is because of the time to reload some data after preemption, right? So it's kind of hard to estimate this. That's why at this moment, at the beginning of the research, we decided to go for a non-preemptive one. It's a more control scenario, let's say. But of course, if you change for a preemptive scheduling, probably will gain more scalability because it's due to the preemption. But on the other hand, it will play a more important role, or it will impact more the cache replacement policy. So we need to study a little bit more this aspect.
Okay, thanks. I have just a curiosity. All these replacement policies, LIP, BIP, DIP, etc., they still present certain level of uncertainty. So is it possible to apply them to hard real-time systems?
Yes, it is actually. There are some papers in the literature that focus on having like static analysis on these policies. Usually, the real-time community goes for a random access or a FIFO. Such policies are easier to have an estimation, right? Yeah.
Mm-hmm. Okay. No, because once I talked with some guys for hard real-time system, they told me, no, we only believe in worst-case execution time because we cannot deal with any kind of uncertainty. That's why I was curious.
Yeah. In fact, what we are aiming, thank you, George, for your suggestion. We now have an architecture, a RISC-V architecture that supports cache partitioning, and we can apply an individual cache replacement policy for each partition. So we kind of go into this direction of having some static analysis for each partition as well, and also considering the preemption.
Okay. Any more questions? No. So thank you again, Bruna and Giovanni. And we go to our next paper. Bye. Next paper is the fourth paper of this session. It's called ETCF, Energy-Aware CPU Thread Throttling and Workload Balancing Framework for CPU FPGA Collaborative Environment. This paper will be presented by Thiago Knorst. Just copy here the link.
Hello, I am Thiago Knorst from the Federal University of Rio Grande do Sul, and I will present the paper ETCF, Energy-Aware CPU Thread Throttling and Workload Balancing Framework for CPU FPGA Collaborative Environments. Nowadays, high-performance applications have imposed an increasing demand on high-performance systems, given the characteristics of these applications such as machine learning, big data, image processing, and scientific computing, for example. To provide better performance, current systems are increasingly using both CPU coupled with FPGAs to process its workloads in order to exploit data and thread-level parallelism from the applications. CPUs usually benefit from the execution of control-oriented kernels, while FPGAs benefit from data-oriented kernels. When both characteristics are present at an application, this heterogeneous system can be utilized in a collaborative way. Collaborative computing surged as alternative, bringing the challenge of how to orchestrate the execution to fully utilize the hardware. HPC systems such as data centers and warehouses have tight energy constraints, which brings the challenge of how to provide the best trade-off between performance and energy consumption. Thread-level parallelism exploitation, TLP, is a manner of increasing performance in CPUs, for example. However, utilizing all CPU cores to execute an application doesn't always provide the best performance or energy consumption. Does this behavior also happen in heterogeneous collaborative environments? To illustrate this behavior, these figures show how the number of threads and workload balancing influences collaborative applications. The system is composed of a 64-core CPU and a data center-oriented FPGA, evaluating performance and energy consumption. The y-axis represents the improvements over single-thread execution, considering an equally balanced workload, while x-axis represents the number of threads executing on a CPU. Workload balance is explored using different values of alpha parameter of the application, which represents the percentage of data each device has to compute. For instance, an alpha equals to 0.3 means that the CPU will compute 30% of the data, while FPGA will compute the other 70%. When alpha equals 0.7, we have the opposite scenario, with 70% of the data being computed by the CPU and 30% to the FPGA. We can notice that the ideal number of threads is different depending on the metric we aim to improve. For both applications, the ideal number of threads for energy consumption is lower than 16 threads, while best performance is achieved using a higher number of threads. The ideal number of threads depends on the workload balance as well. Each STO, for instance, presents best performance using 27 threads when alpha is 0.3. However, when alpha is 0.7, best performance is achieved when using 60 threads. It is also important to notice that using all available hardware threads doesn't provide the best improvements for any of these collaborative applications, besides such a strategy being commonly used by the programmers. Given that, choosing the right number of CPU threads and an ideal workload balance in collaborative applications can improve both performance and energy consumption. So, how can we automatically tune the application to execute with the optimal workload balance and number of threads? Here we present the agenda of this presentation, following with our proposal, the TCF, the methodology, the results, the conclusions and future works. Considering the room for improvements previously discussed, this work proposes ETCF, Energy-Aware CPU Thread Throttling and Workload Balancing Framework for CPU FPGA Collaborative Environments. ETCF is able to transparently select a near-optimal number of CPU threads at runtime. It can also provide a near-optimal workload distribution for a given CPU FPGA environment. Our framework permits the user to select the preferred metric to be optimized as well. This figure shows a high-level view of ETCF framework. The framework administrator is responsible for providing an application that uses OpenCL with data partitioning technique, which assigns CPU and FPGA to compute portions of the data at each device. The administrator is also responsible for selecting the framework's optimization mode and optimization goal. The optimization goal can be selected from these following metrics: performance, energy consumption, or EDP, which is a trade-off between performance and energy. While the optimization modes select which techniques will be applied to optimize the execution. Given these parameters, ETCF will deal with the workload balancing or thread throttling techniques to optimize the execution of the collaborative application. ETCF offers three optimization modes: the workload balancing mode, which is a static offline approach, the thread throttling mode, a dynamic online approach, and the full mode, a hybrid approach that comprises the aforementioned modes. Getting into more detail about the optimization mode, the workload balancing mode is an offline mode which receives the application binary and the optimization goal from the administrator. Then, ETCF automatically adjusts the workload balancing of this application. This adjustment is done by varying the alpha parameter of the application, which represents the percentage of data each device has to compute. To find the optimal alpha, ETCF runs the application parallel region using different values of alpha, evaluating the performance or energy consumption of the system. In this example, performance is evaluating by measuring the execution time. It starts by executing the corner cases with alpha equals to 0.1 and 0.9, aiming at finding which device fits best the given application. If 0.1 provides bad results, search will continue testing 0.2, 0.3 and so on, increasing alpha in steps of 0.1. Otherwise, it will continue with 0.8 in a decreasing order, with 0.7, 0.6 and so on. The search will continue until the results from a given iteration are within a 5% margin compared to the previous iteration. When it occurs, ETCF overwrites the parameter alpha of the source code in order to provide a near-optimal workload balancing considering the tested hardware. Another ETCF optimization mode is the thread throttling mode. which adjusts the number of CPU threads the collaborative application will assign to the CPU at runtime. This mode requires the use of a set of C++ functions in the source code that are responsible for defining the boundaries of the parallel region, collecting runtime data, and adjusting the number of threads accordingly. This figure shows a high-level view of the thread throttling mode, considering the execution of a parallel region and its loop iterations. The execution time of an iteration is defined by the device that takes longer to execute. ETCF will change the number of threads at each loop iteration in the learning phase, collecting data from each iteration until CPU and FPGA execution times match. Consequently, energy consumption will decrease since the iterations take less time to execute. After ETCF concludes its learning, the remaining iterations of the application will execute using the optimized number of threads. The learning phase of ETCF is done using a hill climbing based algorithm. Firstly, it executes with the maximum number of threads available, then reduced to half of the maximum. From then on, it increases or decreases the number of threads to climb the EDP convex function until the 7th iteration. It means that if a certain number of threads result in a lower EDP than the previous iteration, the algorithm takes the opposite climbing direction. We choose this algorithm because it is able to rapidly converge to a near optimal number of threads. The last optimization mode offered by ETCF comprises both workload balancing and thread throttling approaches. In this mode, at each iteration of workload balancing search, the thread throttling approach is triggered to find the near optimal number of CPU threads to that specific alpha. This way, ETCF can maximize the benefits of the collaborative execution by fully utilizing the heterogeneous hardware resources. Following our agenda, now we're going to present the methodology used in this work. Our execution environment is composed of a 64-core AMD Ryzen CPU and a Xilinx Alveo U2000 FPGA with more than 1 million LUTs. The execution time of the applications was measured using the time library from Linux. CPU power was acquired using AMD's hardware counters, and FPGA power was gathered using Xilinx Vivado tool. The benchmarks used in this work are from Shy Suite, which focus on collaborative execution. It uses OpenCL to take advantage of heterogeneous architectures, while CPU parallelism is exploited using C++ thread library. The benchmarks used in our experiments are described in the table below. They represent different types of applications, such as image processing, streaming, and math, for example. In order to evaluate the gains provided by ETCF, we evaluated using the following scenarios. Max threads uses the maximum number of hardware threads available and an equally balanced workload between CPU and FPGA. We will use this scenario as the baseline, since it is the most common approach in HPC applications. The application default scenario uses the workload balance and the number of threads set by the programmer of the application. The Oracle scenario represents the optimal workload balance and number of threads gathered through an exhaustive search. And the scenarios using ETCF framework and its 3 optimization modes, ETCF thread throttling, ETCF workload balance, and ETCF full mode. The next topic in our agenda will show the results gathered from the experiments. This chart shows how workload balance and number of CPU threads can influence the performance and energy consumption. The colored line represents EDP using alphas from 10 to 90%. The y-axis represents the relative EDP compared to the max threads using 50% alpha baseline, while the x-axis represents the number of CPU threads. HSTI shows greatest EDP when the number of threads is lower than 16, while the workload balance has minimum influence on the results, since the different values of alpha present similar EDP. The application HSTO shows greatest EDP when executing with 40 CPU threads, with some influence of workload balance. In PAD application, on the other hand, workload balance has big influence on the EDP, since different alpha values show very different results, while SC presents a mixed behavior, since the workload balance and the number of threads have a considerable impact on the EDP. Alpha values above 60% present similar results with around 30 threads, but EDP is degraded when increasing the number of threads beyond this point. Now we investigate how the optimization goal can vary the optimal number of threads. Taking HSTO application as an example, when considering energy as optimization goal, we have the ideal number of threads with only 12 threads. However, when considering EDP as the optimization goal, the ideal number of threads is 41. Now, this chart shows the performance evaluation of ETCF. Once again, the speedups are normalized to the max thread scenario, using 0.5 alpha, which means that half of the data is processed by each device. The x-axis represents the speedups, while the y-axis represents the benchmarks with the average of them at the end. It is important to notice that for this chart, higher is better. We can notice that the results vary according to the application. VS and RSCD, for example, have big improvements when applying workload balance technique, while HSTI and SC, on the other hand, present biggest improvements when applying the thread throttling technique. On average, ETCF provides above 6.7 times of speedup compared to the baseline. It is also capable of providing similar improvements to the Oracle, which proves that ETCF can provide a near-optimal solution. The biggest difference between ETCF and Oracle occurs on executing HSTI, where ETCF has 4% lower improvements than the Oracle, but still has 10 times the performance of the baseline. This chart shows the energy consumption evaluation using the same parameters as the performance evaluation. It is important to notice that for this chart, lower is better. The results are similar to the performance, since the reduction in execution time also reflects on energy consumption. On average, ETCF reduces the energy consumption on 77% of max threads baseline. Finally, the energy delay product evaluation, which is the trade-off of the previously discussed metrics. For this chart, again, lower is better. Given the discussed improvements in performance and energy consumption, EDP has bigger improvements. On average, ETCF has 93% of EDP reduction and up to 97% of reduction on said benchmark. In this table is shown the amount of time taken from the Oracle and our framework to reach the solutions. Time to solution is a very important evaluation, especially for ETCF thread throttling approach, which operates at runtime, being capable of reaching the solution in less than 1% of Oracle time. Our full approach is capable of reaching its solution in only 3.5% of the time in the worst case scenario, taking only 3.3 on average. This behavior occurs because the exhaustive search suffers from a combinatorial explosion to find the optimal workload balance and number of threads. Back to our agenda, we will conclude the presentation and present the future works. So, we have proposed ETCF, an approach that is capable of balancing the workload and determine a near optimal number of threads for the CPU in a CPU FPGA collaborative environment. The proposed approach shows an average of 93% of EDP savings over the execution with maximum number of threads and an equally balanced workload, while providing similar results to an Oracle in a feasible time. And for future works, we intend to extend the current version to use other thread libraries and use FPGA optimization techniques to enhance the design space exploitation. Thanks for your patience and feel free to ask questions.
Okay, then questions for Thiago. Thank you, Thiago, for your presentation. No questions. Tadeu Nogueira, one question for you, Thiago. Hello. Which Linux library was used to measure execution time?
It was time library from Linux. It was the time library default from C++ applications, included by the headers of the application.
Okay. It's okay, Tadeu? All right. More questions? No. Just one here, Thiago. I will put two questions for you, Madam Most, not to delay so much, but I was curious about, is there a reason not to use always the full mode optimization? Always both optimization modes?
Yeah, because this full mode is a hybrid mode that the framework administrator has to run at the offline mode. That workload balance mode has to run offline. So if the programmer of the application wants to release the binary for, I don't know, maybe another more users and don't know this hardware, you will know just at runtime, so it can apply only the throttling approach. That is an online mode that will adapt accordingly to the system that is running, and so it will not be viable for the programmer to test every system its clients has. So if the user wants to use the full mode, it has to run at the offline mode. So this choose between these modes are because of that. If you prefer to don't modify the binary, so just run the workload balance approach that don't require the
I think you freeze, Thiago. Oh, okay, that's okay. Just wait a few moments if Thiago can come back. Okay. Oh yeah, okay. Now it's cool. You can proceed.
Okay. I don't know if I answered the question.
Yeah, okay, it was okay. Very nice. Okay then. Thanks again, Thiago. And we go to our next presentation. Let me see here. Now we have two presentations in Portuguese. So we should switch to Portuguese. Então vamos para o próximo paper, que é um full paper em português, chamado Predição de cargas de trabalho de nós de computação em nuvem usando modelos ARIMA e redes neurais recorrentes tipo LST. Quem vai apresentar é o Danilo Santos. Aqui.
Olá, eu sou Danilo Santos, aluno do mestrado do Programa de Pós-Graduação em Engenharia de Sistemas e Produtos do Instituto Federal da Bahia e vou apresentar o artigo intitulado Predição de carga de trabalho de nós de computação em nuvem usando modelos ARIMA e redes neurais recorrentes tipo LSTM. Este trabalho foi desenvolvido em conjunto com o professor Alan Freitas. Este é um breve roteiro do que veremos nessa apresentação. A facilidade de disponibilização de recursos computacionais que podem ser provisionados com o mínimo de esforço favorece a adoção do modelo de computação em nuvem. No entanto, a infraestrutura necessária para aproveitar serviços com uma disponibilidade satisfatória gera custos aos provedores de ambiente de computação em nuvem. Ferramentas de gerenciamento de estados de hosts em clusters computacionais como o Cloud Energy Server e o Cloud GI são soluções que permitem um melhor gerenciamento desses ambientes. No caso do Cloud Energy Server, por exemplo, ele utiliza informações do ambiente para avaliar se os recursos são suficientes naquele momento e decide adicionar ou remover hosts do cluster. Aqui neste diagrama de componentes, ele mostra um ambiente típico de computação em nuvem baseado em infraestrutura como serviço que contém um componente que é o controlador, e existem diversos hosts com ports que são responsáveis pelo poder computacional do ambiente da computação. Em paralelo a este ambiente, adicionamos aqui o Cloud Energy Server, que ele é responsável por monitorar as informações do ambiente, fazer verificações periódicas do poder da capacidade de processamento, ou seja, o percentual de processador, o percentual de memória RAM, e a depender da situação do ambiente, ele pode ligar novos hosts para esse ambiente, fazendo uma escalabilidade horizontal, bem como ele pode desligar hosts que estejam ociosos. O funcionamento dele, né, de uma forma de exemplo, aqui nós temos aqui, ao decorrer do dia, o percentual de memória RAM ou de processador, elas podem oscilar durante o dia, e, por exemplo, ao atingir 80%, o Cloud Energy Saver ele pode ligar mais hosts para poder aumentar a quantidade de máquinas do ambiente. Bem como ele também pode desligar hosts caso ele entenda que está tendo uma subutilização do ambiente. Então, para visando economizar energia, alguns hosts podem ser desligados. E se pudéssemos prever cargas de trabalho futuras? A ideia é utilizar modelos preditivos para encontrar carga de trabalho e tomar decisões proativamente. Com os dados dos registros históricos de carga de trabalho dos hosts, processador, memória RAM, podemos aplicar técnicas estatísticas e de aprendizado de máquina para prever essas cargas de trabalho. Caso uma predição atinja algum threshold, uma decisão já pode ser tomada, seja de ligar ou de desligar hosts, por exemplo. Existem diversas técnicas preditivas de séries temporais. No entanto, neste trabalho, utilizaremos apenas os modelos ARIMA e a rede neural recorrente, com células LSTM, por questões de delimitação do escopo e também pela limitação do ambiente onde os experimentos estão sendo executados. O modelo ARIMA de Box-Jenks é muito utilizado na predição de séries temporais. Ele é uma combinação de alguns modelos estatísticos, o modelo autorregressivo, o modelo de médias móveis e a diferenciação que pode ser aplicada para tornar a série temporal estacionária. Veremos logo à frente como definir esses parâmetros desse tipo de modelo preditivo. A rede neural recorrente é uma das técnicas de aprendizado de máquina encontrada dentro da grande área de conhecimento da inteligência artificial. A rede neural recorrente ela se mostrou ineficaz em alguns conjuntos de dados de longo intervalo. Por esse motivo, foram adotadas células do tipo LSTM, fazendo com que a rede ela tenha memória de longo prazo. Antes de aplicar as técnicas preditivas, é necessário realizar uma análise no conjunto de dados, visando identificar algumas características e fazer ajustes para adequar aos modelos preditivos. No experimento foi utilizado o conjunto de dados do grupo Alibaba, com dados reais de carga de trabalho de 4.023 hosts, que foram disponibilizados em um arquivo de 9 GB. Estes dados foram tratados antes de serem submetidos aos modelos preditivos, e aqui você pode observar como os dados brutos se encontram, o calibre de tempo e os percentuais de processador, de memória RAM e outras informações aqui que não foram úteis durante esse trabalho. O tratamento dos dados foi realizado com a linguagem de programação Python e a biblioteca Pandas. Após separação, identificamos que muitos hosts tinham um intervalo de registros faltantes e irregulares. Por esse motivo, trabalhamos apenas com dados de 3 hosts, que possuem maiores quantidades de registros. E aqui vocês percebem que aqui o arquivo ele foi quebrado em arquivos individuais de cada máquina e fizemos as transformações aqui seguindo essas etapas. E ao final de todo esse processo aqui, o arquivo final de cada host ficou apresentando apenas o calibre de tempo, intervalado a cada 5 minutos, e o percentual de processador. Uma das características observadas no conjunto de dados foi a estacionariedade, que pode ser percebida visualmente quando os dados de uma série se mantêm em torno de uma média, como se pode visualizar aqui. Também podemos identificar a estacionariedade a partir da técnica Augmented Diffusion, onde submetemos uma série temporal e ele nos retorna um p-value. Esse p-value pode ser menor do que 5%. Se este p-value for menor do que 5%, a série ela é estacionária. No caso dos 3 hosts que foram submetidos, apenas a máquina 103 demonstrou a estacionariedade, o que significa que não será necessário aplicar a diferenciação do modelo ARIMA mais adiante. No momento do pré-processamento dos modelos, os dados eles são divididos em 2 partes, sendo a primeira o conjunto de treino, que será utilizado para treinar o modelo, então essa parte em azul aqui, e o conjunto de testes aqui em laranja, que será utilizado para comparar com os resultados do modelo preditivo. e assim permitir calcular a taxa de erro entre a predição e o dado real do teste. Agora passaremos para os experimentos, onde submeteremos o conjunto de dados aos modelos preditivos. Antes de aplicar os modelos ARIMA e a rede neural, faremos uma predição ingênua, também conhecida como naive. Para esta predição ingênua, faremos uma simples repetição do último valor conhecido. Por exemplo, se neste exato momento o percentual de uso de processador está em 21%, então eu prevejo ingenuamente que daqui a 5 minutos o percentual será mantido em 21%. Então, daqui a 5 minutos saberemos o valor real e então será possível comparar esse valor real com o valor previsto ingenuamente. E a partir daí a gente consegue calcular uma taxa de erro comparando esses dois valores. O objetivo ao final é que as taxas de erro dos modelos ARIMA e LSTM sejam melhores do que este modelo ingênuo que estamos calculando aqui. Para validar a assertividade das predições obtidas em relação aos valores reais, utilizamos a métrica da raiz do erro quadrático médio, ou do inglês Root Mean Squared Error, a sigla RMSE, que consiste na raiz quadrada da variância média entre os valores reais e os valores preditos. Com esta métrica, quanto menor o valor do RMSE, melhor é a acurácia do modelo preditivo. Trataremos agora do modelo ARIMA. Para a implementação deste modelo, utilizamos a biblioteca StatsModels do Python. De forma geral, o ARIMA recebe esses três parâmetros. O P, que representa o componente autorregressivo, o D, que é a quantidade de diferenças que podem ser aplicadas para tornar a série temporal estacionária, caso ela não seja, e o Q, que é o componente de médias móveis. E aqui abaixo vocês visualizam alguns exemplos de como o ARIMA pode ser parametrizado. Para identificar os melhores hiperparâmetros, utilizamos a técnica do Grid Search, com os seguintes intervalos de busca em cada parâmetro. Então, entre os intervalos de busca do parâmetro P estão esses valores, no parâmetro D esses valores e o Q esses valores. Durante a execução do Grid Search, são testadas todas as combinações possíveis e são obtidas algumas taxas de erro de cada combinação. O objetivo é saber qual é a melhor combinação que apresenta a menor taxa de erro. Ao final da busca, os melhores parâmetros identificados para o modelo ARIMA do experimento foram estes aqui. Então, para cada conjunto de dados, ele apresentou uma determinada combinação de parâmetros que apresentaram o melhor retorno. Após identificar os melhores parâmetros, os modelos foram executados e podemos perceber que as predições obtidas conseguiram acompanhar os valores reais dos conjuntos de testes. Então, você consegue perceber aqui que as predições na linha laranja estão bem próximas dos valores reais do conjunto de testes. Passamos agora para a rede neural. A modelagem da rede neural ela é mais complexa, porque envolve mais etapas como o pré-processamento dos dados, configuração das camadas e os hiperparâmetros, além do treinamento e a posterior predição. Utilizamos a biblioteca Keras do Python, que já traz uma estrutura e facilita a implementação da rede. Para a identificação dos melhores hiperparâmetros, também utilizamos técnicas de Grid Search e realizamos a busca com os seguintes intervalos de cada parâmetro. Então, para a entrada, a gente deixou aqui como 12, nós testamos esses intervalos aqui, a quantidade de épocas, esses valores, e os tamanhos bets, essas quantidades aqui. Ao final da busca dos melhores parâmetros, identificamos que a rede LSTM do experimento teve esses melhores resultados aqui para cada conjunto de dados. Depois que identificamos os melhores parâmetros, os modelos foram executados e podemos perceber que as predições também elas conseguiram acompanhar os valores reais do conjunto de testes. Então aqui novamente, no caso do LSTM, nós temos as previsões acompanhando os dados reais de cada conjunto aqui que foi testado. Diante dos resultados, observamos que os modelos ARIMA se mostraram ligeiramente melhores do que os modelos LSTM e o NAVE. Além disto, o modelo LSTM também se mostrou mais assertivo do que o modelo NAVE. E aqui nessa tabela aqui, é possível ver claramente que cada um dos conjuntos de dados, o modelo ARIMA, ele se saiu melhor em comparação aos dois outros modelos. Como considerações finais, entendemos que a aplicação de modelos preditivos ARIMA e LSTM demonstra ser uma abordagem interessante para identificar cargas de trabalho futuras em custos computacionais. Além do ARIMA e do LSTM, existem outras técnicas que podem ser aplicadas na predição de cargas de trabalho computacionais. Devido a isso, visando a replicabilidade e comparação, disponibilizamos o código-fonte do experimento e as instruções aqui nesse link do GitHub. Além disto, como trabalho futuro, estamos buscando o desenvolvimento de um componente previsor que será incorporado à solução Cloud Energy Saver, que citamos logo no início dessa apresentação. Com isso, pretendemos que a ferramenta ela seja capaz de tomar decisões proativas, considerando as cargas de trabalho futuras em um ambiente computacional. Então, essa imagem que a gente apresentou no início dos slides, esse aqui é o componente Cloud Energy Saver, e a proposta é desenvolver um componente previsor para poder justamente tomar decisões baseadas em dados futuros de carga de trabalho. E aqui estão algumas referências que foram utilizadas na elaboração dessa apresentação. Gostaria de agradecer a todos pela atenção e estou disponível para dúvidas. Pode entrar em contato aí através desse e-mail e muito obrigado.
Ok, obrigado, Danilo. Perguntas para o Danilo? Nenhuma pergunta? Ok, Danilo. Devido a uma pequena pergunta, devido às características, né, dessa rede neural recorrente LTFM, tu acha que para que tipo de séries temporais poderia haver uma chance do modelo usando rede neural ser superior a um modelo como o ARIMA?
Bem, eu acredito que o LSTM ele tem realmente, né, o potencial de até superar, né, depende muito também do conjunto de dados e da extensão, né, do conjunto de dados que vai ser utilizado. Nesse experimento em específico, a gente acabou adotando um recorte do conjunto de dados para poder fazer um resultado, né, de um laboratório, na verdade, um resultado bem específico mesmo. Aí, de qualquer forma, a gente consegue perceber que o modelo ARIMA ele consegue também ser utilizado, né, além dos modelos LSTM que hoje, né, que é a grande tendência de cada vez mais utilizar, né, inteligência artificial para poder a gente fazer essas predições futuras, mas a ideia de trabalho é justamente essa, né, de pegar um recorte para poder demonstrar que é possível também fazer.
Tá, ok. Obrigado. Tem uma pergunta aqui do Jorge, eu vou ler para você. Compararam com algum trabalho relacionado? Se não estiver enganado, há vários trabalhos na área de economia, energia, maximização de desempenho, etc. Houve algum estudo comparativo nos experimentos? Ou há algo que torna esse trabalho muito diferente dos demais?
Bom, existem alguns trabalhos, né, nas buscas que a gente fez, relacionado à previsão de carga de trabalho especificamente. Não cheguei a buscar em outras áreas de conhecimento, nessa previsão de séries temporais. E nesses trabalhos a gente encontrou, né, alguns trabalhos que trazem essa questão de previsão. No entanto, se tive dificuldade em fazer esse tipo de comparação, justamente a limitação de acesso ao próprio conjunto de dados mesmo. Então, e o modelo em si, né, o modelo, a acessibilidade do modelo, alguns trabalhos estavam bem restritos. Então, a gente teve essa dificuldade de conseguir e equiparar, né, a esse formato que a gente está adaptando. A gente poderia fazer uma comparação, mas não seria uma comparação justa, né? Seriam cenários bem diferentes.
Eu estou complementando aqui a fala do Danilo.
Ok.
Pessoal, assim, a gente tem um problema clássico, né, na nossa comunidade de reproduzibilidade de dados. Eu acho que isso é bastante conhecido, né? Então, a gente achou esse dataset do Alibaba, né, que a gente consegue brincar um pouco com ele. A gente vai, na verdade, o Danilo, em um trabalho anterior, quando ele ainda fazia especialização, a gente produziu um artigo e que a gente trabalhava, de fato, com economia de energia no protótipo que a gente publicou no Salão de Ferramentas do SBRC. E esse outro trabalho, a gente está trabalhando somente com a predição de carga, né? O próximo trabalho dele, que vai juntar essas duas coisas, né, é trazer o módulo de predição, que a gente usava uma abordagem com alguns set points fixos, para a ferramenta de gerenciamento de energia. E aí eu acredito que a gente vai, inclusive, fazer uma análise um pouco mais cuidadosa dessas questões aí que o George está trazendo, né? Mas eu concordo, né, quando faz essas comparações, embora a gente nem sempre tenha os dados acessíveis ou todas as condições de contorno que os autores publicaram, mas é um trabalho que a gente precisa fazer essa comparação. Obrigado.
Ok, obrigado. Mais alguma pergunta? Não? Ok, agradecemos novamente ao Danilo, ao Alan. Né? E a gente vai então para o último artigo da nossa sessão, segunda sessão aqui. É um work in progress, né? Um artigo então um pouco mais curto, chamado Paradigma Orientado a Notificações aplicado à Programação de Microcontroladores. E esse artigo será apresentado pelo Lucas Vilela Santos de Maman.
Oi, boa tarde a todos. Eu me chamo Lucas e eu vou apresentar para vocês o artigo intitulado Paradigma Orientado a Notificações aplicado à Programação de Microcontroladores. Primeiramente, eu vou falar um pouco sobre as motivações que levaram ao desenvolvimento desse trabalho. O Paradigma Orientado a Notificações, o PON, é um novo paradigma que foi criado por Jean Simon e por seu grupo de pesquisa, e ao analisar a literatura desse grupo, nós notamos que ainda não havia muitos trabalhos que buscavam aplicar o PON a hardwares microprocessados específicos. Por isso, nós decidimos testar se o bom desempenho que o PON teve em hardwares mais robustos também se aplicava a essas plataformas com recursos mais limitados. Uma outra motivação do trabalho foi a intenção de aproximar mais o PON de aplicações de IoT, já que ela tem uma grande conexão com os conceitos que são implementados pelo PON. Bom, antes de falar mais sobre o trabalho em si, eu vou dar uma visão geral do que é o PON. Como o nome indica, ele é um paradigma e que busca ser uma alternativa a alguns paradigmas que já existem, como, por exemplo, o imperativo. A ideia central do PON gira em torno de elementos que são reativos e que podem enviar e receber notificações. Então, do lado direito da imagem, nós temos os elementos que são ligados à parte lógico-causal, que são aqueles que avaliam as regras do sistema, e do lado esquerdo nós temos os elementos que são factores execucionais, que são responsáveis por modificar o estado do sistema. E esses elementos se comunicam por meio de notificações que só ocorrem quando há alterações no sistema, ou seja, evita processamento desnecessário. Para dar uma ideia melhor de como o PON funciona, eu trouxe esse diagrama que mostra uma sequência de notificações e alterações dos estados. Primeiramente, o sensor 1 é ativado por meio de algum estímulo externo e faz com que a primeira premissa seja ativada, mas a regra, como um todo, continua sendo falsa. O segundo sensor, então, é ativado, tornando a regra verdadeira, e isso faz com que os métodos para ativar os atuadores sejam instigados. Os métodos vão ativar os atuadores, e os atuadores vão modificar o ambiente de alguma forma, fechando um ciclo de notificações. Nesse ponto, o sistema chega a um equilíbrio, então não há mais notificações sendo disparadas. Em algum outro momento, o sensor 2 vai receber um estímulo externo, fazendo com que ele seja desativado, e isso faz com que a primeira regra se torne falsa, mas a segunda passe a ser verdadeira. E isso faz com que os métodos para desativar os atuadores agora sejam instigados, eles vão desativar os atuadores, e por fim o sistema vai chegar a um novo equilíbrio e vai permanecer assim até que haja novas mudanças de estado. Então, tendo essa visão geral sobre o PON, nós podemos passar para o sistema em si que foi proposto. O sistema é formado por sensores e por atuadores, todos eles conectados através de uma rede ou uma central controladora, e a central possui um chip microprocessador. No nosso caso, os sensores e os atuadores foram simulados no computador, mas eles continuam sendo conectados via rede central. E a central foi implementada em um Arduino, tanto em PON quanto C++, e em outro momento foi simulada em computador tanto em PON quanto C++. A lógica de controle dos atuadores é bem semelhante à que foi apresentada no diagrama anteriormente. Ela tem um número pré-definido de sensores que são conectados por uma lógica E e que ativam o mesmo número de atuadores. Já a lógica de desativação a única mudança que ocorre é que os sensores são conectados por uma lógica OR. Nós fizemos alguns testes com diversas combinações do sistema que eu acabei de apresentar, e para avaliar os resultados nós usamos as métricas análise do código gerado, tempo de resposta do sistema e a quantidade de dados enviados através da rede. Então, passando para os resultados, o primeiro resultado que nós temos é quanto ao código em si. Como se pode ver nessa tabela, os códigos em C++ são mais simples, eles necessitam de menos linhas e, portanto, ocupam menos memória. Por outro lado, o POM ocupa mais memória devido à sua estrutura, que é um pouco mais complexa, mas essa estrutura é quem evita as redundâncias e o processamento desnecessário. Os próximos resultados são quanto ao tempo de processamento da lógica, usando tanto C++ quanto o POM em um microcontrolador. Aqui eu quero ressaltar dois pontos interessantes. O primeiro é que o C++, as barras em azul, praticamente não alteram o tempo de processamento independentemente do cenário, mas o POM altera. E isso é porque o C++, sem otimização, é claro, necessita verificar as condições o tempo todo para decidir se deve ou não ativar os atuadores. Já o POM só processa quando há notificações, quando há alterações. Então, no gráfico mais à esquerda, as regras que nunca se tornam verdadeiras não chegam a gastar muito tempo porque não são verificadas pelo POM. E nos demais gráficos, as regras se tornam verdadeiras em alguns momentos e por isso elas gastam um pouco mais de tempo de processamento, mas ainda assim muito menor do que o pior caso. Outro ponto que eu quero ressaltar é que tanto o POM quanto o C++ têm aproximadamente o mesmo desempenho para o pior caso, que são as duas primeiras barras de cada gráfico. E esse pior caso é quando todas as regras têm que ser avaliadas. Mas o POM melhora bastante o desempenho para as regras que são mais complexas, o que pode parecer contraintuitivo até, mas isso acontece porque essas regras se tornam verdadeiras com menos frequência, e, portanto elas são avaliadas também com menos frequência. O último resultado que eu gostaria de trazer é quanto ao tráfego de dados, que acaba sendo uma consequência dos resultados anteriores. O C++, novamente, sem otimizações, não guarda os estados do sistema e nem filtra quem deve ser ativado ou não. Por outro lado, o POM faz isso sem nenhum esforço adicional do programador. Para uma aplicação que necessita enviar dados pela rede como essa, o C++ acaba congestionando mais a rede porque ele envia continuamente atualizações até para atuadores que não precisam. Já o POM tem esse conceito implementado na sua estrutura, o que minimiza o número de notificações e, consequentemente, também minimiza bastante o tráfego na rede. As conclusões que nós tiramos, então, desses resultados são basicamente que, primeiramente, nós verificamos que sim, é possível utilizar o POM em uma plataforma microprocessada, mas o LingPOM, que foi utilizado, ainda precisa de melhorias para facilitar mais a programação. Também nós verificamos que os resultados e os benefícios do POM são condizentes com o que há na literatura para as outras plataformas. E o terceiro ponto que nós observamos é que o POM, de fato, ajuda a reduzir o processamento, que implica também uma redução de consumo, o que é um fator bastante importante para essas plataformas com recursos mais limitados. Por fim, algumas visões de trabalho futuro que nós temos são a melhoria da sintaxe e funcionalidades que são implementadas no LingPOM namespace e também da sua derivação para as plataformas microprocessadas. Outra possibilidade de continuidade desse trabalho é fazer a implementação e análise de aplicações mais complexas, envolvendo também sistemas maiores. Bom, essa era a visão geral que eu queria apresentar sobre esse trabalho. Eu agradeço a todos pela atenção e eu fico à disposição para questões e discussões. Obrigado.
Ok, obrigado. Lucas, perguntas para o Lucas? Tem perguntas? Só fazer uma perguntinha aqui, então. O Lucas, em relação à escalabilidade, que conclusões vocês podem chegar? É possível que se obtenha resultados similares para qualquer número de sensores e atuadores, considerando esse tipo de plataforma que vocês testaram?
Sim, uma das ideias principais do POM também é a escalabilidade, né? Que a ideia é que com pouco código você possa só aumentar, por exemplo, o tamanho de um vetor e escalar o sistema inteiro, né? No caso de usar um hardware microprocessado, tem o problema da escalabilidade do hardware, claro, né? Até por isso nós não usamos muitos dispositivos, né? Mas, na teoria, os resultados se mantêm, não importa o número de elementos que estiver no sistema. Porque, claro, o tempo total vai aumentar, né, obviamente, mas a média se mantém porque ele é projetado para atuar com notificações, e todas as notificações vão se manter as mesmas. Né?
São escaláveis. Ok, obrigado. Mais alguma pergunta? Ok, não. Ok, então, obrigado, Lucas, pela apresentação. E então esse era o último paper da segunda sessão, a gente encerra a sessão. Vamos ter um coffee break um pouquinho maior, porque estamos 10 minutos adiantados, só que um coffee break, home coffee break, né? Ok? Então, até a próxima sessão, que é às 15h30. Um grande abraço a todos.